Okay, welcome to ECE 164, Analog Integrated Circuit Design, Lecture 6 on common gate and common drain transistors. So far in this class, we've talked about the common source transistor quite a bit, and we've built up the frequency response of this. Today, I want to introduce two additional circuit blocks, that is a common gate transistor and a common drain transistor. Okay. Now, notably, and understandably, they get their name from the fact that they share this common terminal. So a common gate, the gate terminal is shared between both the input and the output. And in a common drain, the drain terminal is shared between the input and the output. So my signal is referenced here at this input. And if we go to network theory, essentially we have a three-terminal device. And so for a two-port network theory, we need one terminal shared. For a common drain, common gate, common source, terminal. Okay. So what we're going to do is we're going to use these other atoms of circuit design, as I'll call them, and we're going to incorporate them into larger amplifier stages, both cascading, that is putting blocks after each other, and cascoding, stacking them on top of each other in order to build better amplifiers. However, fundamentally, whenever you're analyzing circuits, we can always decompose them into these kind of core building blocks, that is common source, common gate, and common drain stages. All right, so let's start by analyzing the common gate stage. Here, we have some bias current IB, and I'm representing this just as a current source. This could be a resistor, could be another transistor. It's simply here to bias up the transistor. Okay? We also have a load resistor RL, okay? And a gate bias VB. Okay, so this is a DC bias source that's biasing the gate to put us in a particular region of operation. The bulk in this case, since this is an NMOS device, it's connected to ground. Okay? And without loss of generality at the input, we have a current source, IN, and a source impedance, or a Norton equivalent impedance of RS. Okay. Now, as we'll see later on in this lecture and in future lectures, a common gate transistor is actually really good for current amplification. Okay. That is, that it acts as a current buffer. There's no gain, but it allows us to transform the impedance at the input and the output. Okay. So in this case, you'll often see common gate amplifiers used with current inputs rather than voltage inputs. Okay. So if we wanted to analyze this circuit, as we've done many, many times at this point in the class, the first thing that we need to do is we need to draw the small signal model. Okay? So I'm going to replace the transistor with the small signal model, and I've already done quite a bit of simplification here for you. Namely, the gate to the drain capacitance and the drain to the body capacitance that normally right here and from here to ground, I've combined these together into one capacitance. They both go to ground. Okay? Now note, unlike the common source stage, where the CGD was problematic in the sense that it coupled our input and our output terminals, it does not do that here. So the common gate stage does not suffer from Miller effect. It does not have this bootstrapping capability with the device intrinsically. Okay. At the input, I've combined, or at this input terminal, I've combined CGS and CSB. Okay. And you'll also notice that we've taken into account the body effect. So since this body is tied to ground and the source is not tied to ground, there is another transconductor, GMB. Okay? However, this transconductor, since the gate is tied to ground, is directly in parallel with GM. So I've simply put them together, and I've called this an enhanced GM. Simply saying that since they are combined together, they have the same polarity, so we get a benefit from the body effect in this case. So our GM prime, if you will, is actually larger due to the fact that we have both gates contributing. Okay. So we're going to have some signal come in here, okay, and the signal is going to be buffered by this transconductor, and then we'll measure the voltage at the output. Okay. All right, so let's analyze this circuit, and we'll start in a couple of different stages. Let's first start by looking at the current transfer function. That is, how does the output current I out relate to the input current I in? So very, very, very simple circuit. We can write a couple of equations and we can draw out the model. If we look into this device, that is, we look into the source of the transistor, we essentially see 1 over GM prime, that is our compound effective GM, in parallel with R naught. Okay. Now, as we've done many, many times in this class, we'll say that GM times R naught is much, much greater than 1, which effectively allows us to remove this R naught. Okay. So in this case, this input current simply sees a dividing. It sees a divider between RS and this impedance 1 over GM prime. We're also going to have a pole, and this pole at the input in terms of frequency response, it's going to be at very high frequency. Okay, simply because 1 over GM prime in parallel with this RS, it's a very low impedance. And this source capacitance here is usually typically small as well. So this stage has very high current gain, or excuse me, unity current gain up to very high frequencies. Now, we can write this transfer function I out over I in. Very simple to write by hand. If you want to convince yourself, you can write KCL here, though. Essentially what we have is we have GM prime divided by GM prime plus this SCS plus 1 plus RS. Okay. So if we didn't have any capacitive effects, that is, if we didn't consider any frequency dependence of this, we would essentially have GM prime RS divided by 1 plus GM prime RS, whereas this quantity is large, right? So if GM prime is large or if RS is large, this quantity in total would be large, much greater than 1, and we essentially get near unity current gain. Okay. We have a single pole in the circuit. This pole is located at this frequency, related to both RS, GM prime, and CS. Okay. Now, as we saw earlier, or we kind of intuitively reasoned earlier, this pole is at fairly high frequency. So this circuit has very good current gain. It acts very much like just a buffer. So it copies the current that's coming in, and it transforms the impedance. So this is a very good stage for a low input impedance. So if we had a sensor that we wanted to connect to, this circuit is very good in the sense that it has a low input impedance, and I could connect this to either a current input or a high output impedance of a voltage source. Okay, so under the condition that we have that the GMRS is much, much greater than 1, this essentially looks like unity current gain up to very high frequencies, essentially up to CS divided by GM as our pole. Now, let's also talk about the input and the output impedances of these different stages. In order to do this, we'll start by looking at the input. Okay, so we can write KCL right here at this input, and we can simply say that I test, that is the current that's flowing in here, is equal to GM prime times V test, that is any current, plus V test divided by R out, that's this current, minus V test, or V out divided by R out. So we can simplify this by looking at the input admittance, that is Y in. Okay? Y in is I test divided by V test, or GM prime R naught divided by RL plus R naught plus this SCS. Okay? Now in this case, this test source that we've put at the input, it's simply equal to minus V test because the gate is grounded. And so VGS is just minus V test. At the output, we can write one KCL equation at the output, essentially right here, calculating V out divided by RL, any current that flows through here, current that flows through this R naught, as well as V test divided by R naught, and this GM prime V test. Now, you'll notice that this term, essentially what we're looking at here is again, that this 1 over R naught is in parallel with this GM. Okay. Another way of saying this is coming back to our GM R naught being much, much greater than 1. This term is essentially negligible when we compare it to this term here. Okay. And we've done the same thing to simplify this expression down here. Okay. So we're going to see this many, many times in this class. And essentially all that we're saying is that the intrinsic gain is much, much greater than 10. This is a very good approximation for most technology nodes until we get down to very, very deep sub-nanometer technologies like 32 nanometers or 20 nanometers. And even there, it's starting to get a little bit better because of newer types of devices, not FET-based devices. So we can use this input admittance and we can convert this into our input impedance simply by taking the inverse of it. So 1 over the admittance is our input impedance. And what we see is that the input impedance is approximately 1 over GM plus this load resistance divided by R naught. Okay? So oftentimes this load resistance divided by R naught, this term here, it's small, and so we approximate this stage as 1 over GM. However, we do have to be careful of the special cases when this is a very large output impedance RL that can actually make the input impedance of this stage quite large. So the two interesting cases, just to highlight them again here, if we have RL, that is the load resistance much, much less than the output impedance of our transistor R naught, the input impedance is 1 over GM prime. And this is a fairly well-known equation. Most people, if you ask them the input impedance to a common gate source or a common gate stage, this is what they'll tell you. It's very correct. However, you also have to be cognizant of this other condition, and that's that if the load impedance RL is large, that is that the stage is trying to buffer a very large impedance, the input impedance can actually be not quite as low as you would like. In this case, it approximates to RL divided by GMR naught. We know approximately what this quantity GMR naught is. In our technology, this is, depending on the length of the transistor, anywhere from about 40 to 100. Okay? So essentially, we're reducing this by 40 to 100 of the load impedance. Okay, so now let's go ahead and let's compute the output impedance. And so here, essentially what I'm doing is I'm trying to find what impedance do I see looking back into this stage. Okay, so this is important again when we talk about the zero value time constants or other methods. If I want to represent this stage, I want to make a model of it, I need to know what the effective output impedance is. So here, we're applying a test voltage source, V test, and measuring I test. So we're simply writing couple of equations here. The current that flows through this transistor is V test divided by R naught plus VGS divided by R naught plus this GM prime times VGS. Okay, and again we're making the exact same simplification that we made before, that GM R naught is much, much greater than 1. That allows us to simplify out this term and neglect it. Okay, in this case we know VGS. VGS, that is this source voltage and this gate voltage. The gate is grounded. Okay, so VGS is simply minus I test. That is the current that we're flowing in up here. It can only go all the way through down here. It has to split, and it splits between this transconductor and this output impedance. Has to come together at this node RS. Okay, and it comes through here. So we know this node voltage VGS is simply minus I test times RS. So we can put this together and write that the output impedance R out is equal to V test divided by I test, which is RO, or R naught, our output impedance, times 1 plus GMRS. Okay. So if we think back, we've actually seen this before. This exact same circuit, identically the same circuit, we analyzed when we were looking at a common source with source degeneration, and we found the exact same answer. Okay. And if we think back, I've hinted at this a few times, we'll talk about it much later in this course, that this is a form of feedback. Okay? And so what happens in feedback is we always have this 1 plus AF term. And feedback can do a couple of things. It can either increase our output impedance, it can decrease our output impedance, but it always does so by this 1 plus AF term, okay, or 1 plus beta if you're used to that terminology. So in this case, the output impedance is going up, and it's going up by our 1 plus AF term here, or our loop gain, which is GM prime times RS. Okay? So what this means essentially is that for a common gate stage, we can have very, very high output impedance, particularly if we have this GM prime RS quantity being much, much greater than 1, okay, which is often a design consideration when we're making this type of stage, that we actually design for this type of criteria. Okay, so now let's look at the time constants of this. So looking at the frequency response, we have a couple of time constants that are pretty easy to pick off. So this input capacitance that we had, CS, if we look into the transistor, we just calculated this. This is approximately 1 over GM. right, for a small load resistance, assuming that we're making this load resistance much, much smaller than R naught. Okay? In this case, the time constant at the input is simply Cs divided by Gm prime. Okay? At the output, we again use zero value time constants. We remove all of the other capacitors, and we try to find the driving impedance. In this case, looking back in here, we see a very large impedance looking down. Okay? And I'm essentially saying that this impedance looking down in parallel with RL is dominated by RL. Okay? So what that means is that I have a very large impedance in parallel with RL, so the impedance here is simply RL. So in this case, we have that the output time constant is CL times RL, okay? And we can combine these two together to estimate the bandwidth of the circuit. All right, so to quickly summarize a common gate stage, a common gate has unity current gain, and it has this current gain, at least with our simple model, up to a frequency that's roughly Gm over CGS, which is Ft of the device. Okay, so it has very, very high current or very high bandwidth for this unity current gain. The input impedance is fairly low. It's 1 over Gm, at least as long as we have the load with a reasonable output impedance. If we have a large load resistance, we know that the input impedance is going to go up, and it's going to go up essentially that the load resistance RL divided by Gm times Rs. Okay. So with this, we also know that you can use this to effectively make a very large output impedance. So in summary, this stage, as we'll show a little bit later in this course, is actually very good for turning a okay current source into a great current source. Okay? Essentially what it does is it buffers the current, so it has this unity current gain property, but it increases the output impedance that we want from a current source substantially. All right, so let's look at an example of this, and this is what's known as cascoding. So cascading, that is with an A, is when we put stages after each other. So on the homework, we've seen a couple of examples where we cascaded amplifiers. Here, what we're doing is we're cascoding. So think about those Russian dolls or the game where you stack the rings on top of each other. Here, we're taking our common source amplifier, M1, and we're sticking this common gate amplifier on top of it. Okay, so this is what's known as a cascoded amplifier. And essentially what we can do is we can take this amplifier, right? We know M1 is inverting our input signal and it's generating relatively high gain. The current that's coming out of M1, right? It's being buffered by M2. And here we're creating a much, much larger output impedance, or an effective output impedance R0. Okay? So we can effectively write a low frequency equivalent of this circuit where we have this GM, this capital GM, and I'm using capital GM here to refer to the compound transconductance. That is, since this is no longer a single stage amplifier, I'm referring to the GM of this entire stage here comprised of both M1 and M2. Okay? Likewise, I have an output impedance R0. Okay? So GM here, if we want to think back to first principles, we simply know that it's the partial derivative of the output, I out, that is the current here, with respect to the input. So said another way, if I wiggle this input voltage VI, how much current change do I get at the output? Okay. So in this case, this stage M2, it doesn't actually add any transconductance. All that it does is it takes the transconductance of M1, that is, M1 converts any little wiggles at this input into wiggles in currents here. M2 simply copies them. Okay? So the compound transconductance for this particular amplifier is simply equal to the transconductance of M1. Okay, so this capital GM is equal to GM1. The output impedance we just derived, we essentially have the output impedance of this device RO2 times 1 plus GM2 prime times the impedance that we see looking down into this device, which is RO1. Okay. Now again, here we're using GM2 prime, we're taking into account the body effect, and we know that this body effect actually helps us in that it gives us larger transconductance. Okay, larger transconductance than if the gate and the source were tied together. Okay, so we can combine this together, and one of the metrics that we used to talk about a single stage amplifier was the intrinsic gain. The intrinsic gain is the product of the transconductance times the output impedance. Okay, so for a single stage, it's just GM or not. Okay? Here, we can take this transconductance and this output impedance, and we can multiply them together to find the intrinsic gain of this structure. Okay? And what we'll see is that effectively, by combining these two structures together, we're able to get GM times R naught squared. Okay? So we can increase the gain of this amplifier by having this common gate stage that effectively increases the output impedance. So the transconductance did not change. The transconductance stayed the same, but what we did is we effectively increased the output impedance due to this cascoded device M2, this common gate device, and this larger output impedance created a higher gain for this particular stage. Okay, this has some other very important benefits that are a little more subtle, and let's talk about a few of these now. So if we look at this stage, so when we had just the common source amplifier, we had CGD, and CGD was a bit of a problem child for us because what it did is it coupled the input node VI and the output node Vout. And so what it did is it effectively created this Miller multiplied capacitance, which we reflected at the input CGDI, and a capacitance that we reflected at the output CGD out. Okay. Now, the gain or the Miller multiplication of this was equal to the gain of the common source stage in our previous example. Okay. So here, the nice thing is that the gain that this sees, or the impedance that this sees looking up here, right, and this is ZX, is effectively much, much smaller than for a common source amplifier. Okay? So what this means is that we essentially get to mitigate all of the problems of the Miller effect. So I still have this load resistance, but I'm hiding or isolating this load resistance from this capacitance with this stage M2. Okay? So effectively, when I look up into this node, I see 1 over GM2, depending on if R is larger than that, or R divided by GM times R naught of this stage. So I've effectively reduced the impedance that I see looking up here minimally by GM times R naught. Okay? So what this means is that I have a much lower impedance that this capacitor sees. Okay? And what this does is this reduces the Miller effect from this transistor. Okay? Now, the other thing that we also saw that CGD caused that was a bit of a problem in our previous design was it created a zero in the transfer function. And it created this zero because essentially what could happen is the signal here at VI could race forward through the output and it would come right to the output through CGD. Okay? This doesn't entirely eliminate this zero. We could work through the exact analysis and we'd find that the zero is still there. But what it does do is it helps to mitigate this problem because essentially now the signal still has to propagate through this entire path. Okay? So the zero actually changes frequencies quite a bit, and we get some of these other benefits. So to recap the benefits of this cascode device, number one, we essentially are able to increase the gain for a single stage amplifier. Okay? This comes at the cost of headroom. So in order to accommodate M2, we had to have more supply room or swing, that is our supply voltage here, in order to account for at least VDS, right? We at least need 1 VOV of M2 to keep this device in saturation. The benefit that we got from that was we improved the frequency response substantially. That is, we mitigated the Miller effect that this saw a very large impedance up here. And we also got increased gain from this stage simply because we have larger output impedance. Okay? So the gain of this entire stage is this compound GM, which we know to just be GM1, times the impedance that we see looking up here, which is R, times the impedance we see looking down, which is R naught. So R parallel R naught times this transconductance GM. Okay, so in order to do this, let's put some numbers to it and we can actually analyze this. We have our input here. We're again biasing this with a DC input VI, applying our small signal VI on top of that. We have some source impedance RI. The device in this case, it's fairly large, 20 micron by 1 micron. In order to keep the example simple, I also made the cascode the exact same size. We'll find out, and you'll get to practice this later in the course, that maybe this isn't the best way to do this. This is certainly one way to do this, but maybe not the best in terms of the frequency response as well as the gain. We're also biasing this with just a voltage source, and we're going to come back and we're going to visit in just actually next lecture. We're going to learn how to bias these amplifiers properly. So we're going to start to get rid of all of these voltage sources that are floating around. Okay. Here, I'm also biasing this just with a current source in order to make this very general and have any kind of load impedance I want. And I have some resistance R, which is tied to VB. Again, this same node such that I can bias and set the bias and the gain independently. Okay. So here's the parameters that I used. VB is 2.5 volts. VI is 1.394. The cascode voltage was 3 volts. This has a bias current of 500 milliamps, so a lot of current, 5 kilo ohms, and an input impedance of 5 kilo ohms. And we want to understand and answer this question, what is the impact of the cascode? Well, one, we know that the bandwidth should increase. We should see less of an impact of this CGD device here, that is the Miller effect. Okay? And this is fairly easy and ready to see if we just do a ZVTC analysis on this. The second one, and this is a little bit more subtle, is that now we're going to have another non-dominant pole. Okay? And this non-dominant pole essentially is going to happen at this node. So we're going to have a pole at the output, we're going to have a pole here, and we're going to have this pole at the input. Okay, this pole, it's typically the non-dominant pole, and that's because the impedance that we see looking up into this device is fairly low. It's 1 over GMC. Okay, so we'll have this device, we'll have a non-dominant pole here, and if we have a output capacitance, we could end up with another non-dominant pole there as well. So we're comparing this to the single stage amplifier that we've been talking about and we designed for the last several weeks. So without the cascode, we see this green amplifier. We have one dominant pole. The dominant pole was roughly at about 32 megahertz, and then we saw that the non-dominant pole was quite high up in here in frequency. It was at a gigahertz or 2. Okay. Now, this blue line shows what happens when we added the cascode. So we haven't changed the input size. We haven't changed anything. All we did was we add the cascode device. Okay? So the first thing to notice is that we have more bandwidth. Okay? And this bandwidth essentially is that we're extending it and we're mitigating the Miller effect. Okay? Now, what you'll notice is that at higher frequencies, that is up here, we actually start to fall off faster. So here we had kind of this 20 dB per decade roll off. And then right at about here, somewhere in here, we hit another pole and we start rolling off at 40 dB per decade. Okay. With our cascode amplifier, we're flat up until about 50 megahertz, and then we hit our first pole, we start to roll off, and then very quickly we start to pick up additional non-dominant poles. So this circuit has 2 non-dominant poles, and so it rolls off very quickly, and that's why the gain starts to fall off very fast here. Okay. The take-home message from this, though, is that simply by adding this cascode, we were able to increase the bandwidth from 32 megahertz to 52 megahertz. So we got about a 62% increase in the bandwidth of the circuit simply by adding this one cascode device. So this is a very powerful technique, and it's used quite often for common source amplifiers and also for current sources, as we'll soon see. Now, the problem is I briefly mentioned about this earlier, and just to kind of come back and dive into this a little bit deeper, is simply that adding this cascode costs us supply room. So if we think about how we would bias this circuit, okay, and that is that even if I adjust this voltage here, VB cas, because VBCAS essentially sets this voltage. And even if I adjust this such that I put this transistor here, right at the edge of saturation, so I minimally have one VOV here, right? I need one VOV here in order to keep both of these transistors in saturation. Okay. Now, we should start to have a feel for what VOV typically is. We're restricted in our design environment by me to have VOV greater than about 150 millivolts. Often, we usually go a little bit more than that. So minimally, we're talking that we've already lost up here about 300 millivolts. Okay. Now, 300 millivolts is not such a big deal. We have a 1.8 volt supply. However, if you were in a very new technology where you only had 0.9 or 1 volts and you were losing 300 millivolts, you would have lost a third of your supply that you can't even use for the signal swing. Okay? So what you'll find is that in older technologies, cascoding and even double cascoding and triple cascoding, where you stack more of these to further increase the gain, was a very viable option when you had a high supply voltage. However, in newer technologies, it's become less common simply because there's not supply voltage or headroom, as it's often called, in order to do this trick. One cascode is typically fine. In newer technologies, you'll rarely ever see more than that, though. Okay, so now let's talk about this last stage. Let's talk about the common drain. So a common drain is also known as a source follower, and we'll see why it's known as a source follower very shortly. So the setup is as follows. We have the drain of the device connected to the supply voltage VDD. The bulk is again grounded. We're using an NMOS. If we were using a PMOS, we'd have the freedom to tie this bulk either to the source or to connect it to VDD. In this case, we have to tie this to the lowest potential, so we're tying it to ground. Our input is coming in the gate. Down at the drain, or in the source rather, we're biasing this transistor with a current source IB. We have some load RL in parallel with CL. Okay. So in order to analyze this circuit, same procedure we've followed for quite a few times now. We're going to replace this with the small signal model. I've done so here, and I've done some simplifications. Namely, the gate to drain capacitance, that is CGD here, and CDB, they're both in parallel, and they're both connected between this input node and ground. Okay? We have CGS, that is the gate to source capacitance connected between the input terminal and the source, which happens to be the output in this device. We have GM, and we have GMB that opposes it in the opposite direction. So we have minus GMB times V out. Okay? We also have our load resistance and our capacitance. So very often we don't have CSB, but in this case we do have CSB, and it turns out to be in parallel with our load capacitance CL. All right, so let's analyze this circuit. And let's start by looking at the transfer function. Okay, so if we redraw this circuit a little bit, we essentially end up with something that looks like this. Okay, now, I've lumped the capacitors together. That is, I've taken this capacitance at the output node and I've called it CL total, which is simply CL plus CSB. RL total is RL in parallel with 1 over GMB. So if we look back at this circuit here, we see that this GMB doesn't depend on my input. It merely depends on the output. So in a sense, this is very much like the diode connected transconductor that we had. This actually looks like a resistor, and it looks like a resistor with a resistance of 1 over GMB. So the load resistance that I have here, RL total, is RL in parallel with 1 over GMB, which is in parallel with R naught. Okay? So oftentimes this is going to be dominated by this relatively low impedance of 1 over GMB, which is certainly much lower than this R naught term. Okay, so writing KCL, this KCL is at this output node here. So I have current that flows through this capacitor SC total, I have current that flows through CGS, and I have current that flows through my load resistance RL total. Okay, I also have this input term of VI in CGS, and I have the GM generating this last term, GMVI minus V out. I can rearrange this after doing a little bit of math, and I'm trying to isolate V out over VI. That is the gain of this stage from the input terminal here to the output terminal. And I get GM plus SCGS divided by GM plus SCGS plus SC total plus 1 over RL total. Okay. So I can massage this around a little bit. Essentially what I'm trying to do is I'm trying to pull out the terms that don't have any frequency dependence, putting them at the beginning, and then having just the frequency dependent terms. Okay. So the DC, or the midband gain of the circuit, and midband simply means that we're not taking into account the frequency dependent effects, is GM divided by GM plus 1 over RL total. Okay. If we look at this and we think about this, another way is we could multiply this RL on the top and the bottom, and we'd have GMRL divided by 1 plus GMRL. Okay. So in this sense, it's actually pretty easy to see that the gain it's very close to 1, right? Depending on the quantities of GM and RL, a typical value may be something like 0.8. Okay. We also have a 0 in this circuit. This happens to be a left half plane 0, SCGS divided by GM. Again, this is very near FT of the device. It's very high frequency. Okay. And I have one pole in this circuit. Okay. Now the interesting thing about the pole is, again, that it depends on this 1 over GM term. So this pole can actually be at very high frequency because it doesn't see a lot of impedance. Okay, so let's look at the low frequency gain. So the low frequency gain, again, we're taking rid of, or not taking into account any of these frequency dependent terms. We know that our total load resistance was RL parallel 1 over GMB parallel R naught. Okay? And we know that from the previous slide we derived that the gain, that is the input to the output transfer function for this device, was GM divided by GM plus 1 over RL total. All right, so there can be 3 interesting cases, and it looks like I apologize, I actually flipped the figure around here. I put a PMOS for you. Regardless, this still holds. We see a couple of interesting cases. One, if we take the load resistance to infinite, essentially this means that we're biasing this with something like a current source rather than a load resistor. We take the output impedance R naught and we take that to infinite. Essentially here we're just idealizing the transistor a little bit and removing the body effect, as you might do if you had a PMOS device and you connected the bulk to the source. Okay. In this case, the gain is actually ideally exactly 1. Okay. This is useful, but it does make a couple of assumptions that don't always hold in practice. Namely, it's very hard to say that the output impedance is infinite and that the load resistance is also infinite. This also can never happen for an NMOS simply because we can't tie the body to the source together, so we can't ever get this GMB term to go away. All right, so if we look at the NMOS case, and this is the case that we've been talking about and we derived this, we can still look at kind of these extreme cases of RL going to infinite and the output impedance going to infinite, but not having GMB be 0. In this case, essentially, the gain is a ratio. It's a ratio of GM divided by GM plus GMB. Okay. We actually know that this ratio, this pops up when we're looking at this threshold voltage, and the ratio between these two, it's often called chi, the Greek letter chi. It's about 0.8 for most technologies. Okay. So we know that in this case the gain can be roughly about 0.8, always less than 1 though. And the third interesting case is if we take, again, the output impedance of this device to infinite, GMB is equal to 0. That means that we're tying the body and the source together, but we have some finite load resistance. This is a very realistic case. We can write that the gain is GM divided by GM plus 1 over RL, or we can multiply this through with the previous example that we had, and that's GMRL divided by 1 plus GMRL. All right, so now let's talk about some of these frequency-dependent effects. Again, we have this 0. The 0 here minus GM divided by CGS, and we have this pole, which is essentially at a very high impedance simply because of the, or very high frequency because it has this low impedance of 1 over GM in it. Now, the interesting thing about this is that depending on where these poles are positioned, we can actually end up with some different scenarios. Okay, so the first one, let's say that the 0 occurs before the pole. Okay, so if we look at the magnitude response, essentially the amplifier will have near unity gain. Okay, then we'll hit the 0, right? And the 0 is going to cause actually a positive 20 dB per decade increase here. And then we hit the pole and we flatten back out. Okay. This other case where we hit the pole first, so here we have near unity gain, we hit the pole, and then the 0 causes us to flatten back out up here. Okay. Now, the interesting, at least academically interesting, not very practical question to ask yourself is, what if the 0 and the pole were at the exact same frequency? Okay. Essentially what you're trying to do, or what we're trying to accomplish with this, is canceling a pole with a 0. Okay, and at least in theory, we could get infinite bandwidth from this. In practice, this is almost never done. It's very hard to ensure that we track these two quantities together. So the pole depends on this load capacitance, which can change, right, depending on what we put after this stage, as well as the load impedance RL total, and the 0 is more or less FT of the device. Okay? So while academically a little bit interesting, this is not a very practical result, although people do occasionally still do this, not exactly in this context, but in other contexts, of canceling poles with zeros. Okay, so let's go through and let's derive the input impedance and the output impedance for this, very much like we did in the previous example for common gate. So one thing that I want to point out, and we need to start becoming good at this, and that's that we have to start to develop some intuition, and we have to start to develop some insight in how these circuits work. So I'm not going to continue to write out KCL and KVL equations on all of these slides. I'm simply going to say that, by inspection we can see this. And by inspection, what I'm simply saying is that, we can actually look at the circuit and make some reasonable assumptions, and we can come to this equation without having to do a whole lot of work. Okay, this is something that, as a good circuit designer, you really need to have, and it does. It takes practice. Okay, so I would encourage you, if you can't figure this out very quickly, write it out. So pause the slides now and derive the input impedance of this device. Essentially, all you would need to do is write a KCL node here, a KCL node here, and then you could solve this. Okay, I'll give you a hint, and the hint is simply that we already know what's going to happen with CGS, and we essentially know the current that's going to come in here. Okay, and we can use that property to very quickly write the admittance. Okay, so that is that we see this capacitance, which we can write the current through this, and we know what happens with CGS in terms of its input and its output terminals. Okay. So I'll leave that as a quick aside exercise if it's not obvious to you how this works. Now again, the gain that we derived, it's nearly unity, and it's nearly unity up to very, very high frequencies. So essentially, at very moderate frequencies, that is, until we get to very high frequencies, the input more or less just looks like a capacitor. And it looks like a capacitor that's composed of CGD plus CGB. So this isn't even a very large capacitor. We are going to see a fraction of CGS, and this comes from this idea of bootstrapping. Okay, so now if we look at a PMOS stage, so we're taking this source follower, and instead of looking at the NMOS, now we're looking at a PMOS. We've tied the body and the source together. Okay, here we're inactivating or turning off this second transconductor because GMB and VSB is 0. Okay, so we essentially have very low frequency gain is 1. And the input capacitance, that is what we see looking into this device, it's again a very small capacitance. So what this means is that this has very large input impedance. Okay? So we've seen two examples, or two extreme examples of amplifiers. The common gate amplifier had very, very low input impedance, and this stage has very, very high input impedance. Okay? So these are very good in the sense that if we wanted to alternate them or cascade them, they have very different properties, and they're useful at different stages or different parts of an amplifier. Okay, so looking at the output impedance of this device, essentially, again, by inspection, we can almost write this, and this doesn't take a whole lot of effort to even see. We have the 1 over GM B, and that's in parallel with this 1 over GM here, okay? And then we have this capacitive divider that's also formed here, right? Now, the trick, it's not really a trick, but it's something that you always have to remember. Whenever you're computing the output impedance, we need to turn off the input. And turning off the input in this case simply means that we're grounding the input. Okay? So the input impedance that we see, or the output impedance we see looking into this device, is these parallel transconductors and these two parallel capacitors. Okay? The nice part about this stage is that this term, this 1 over GM term, it dominates, and so it's very low output impedance up to very high frequencies. Okay? So we'll talk about the benefits and the use cases of this type of stage in just a few slides. Now, what happens if we have some source impedance? Okay, so in the previous slide, when we derived it here, we didn't have any source impedance. And this is a very idealistic case that we're using ideally an ideal voltage source to drive this stage. Okay, so now what we're doing here is I've added some finite source impedance, okay, Ri. And this we cannot just simply do by inspection. Now this complicates this quite a bit, and essentially it's because some voltage can form at this gate terminal. This gate terminal is not necessarily zero, which complicates our output impedance. Okay, and we're going to see some interesting cases occur when we do this. So to proceed with the analysis, we're simply going to write that the output impedance Zx is equal to V out divided by Ix. Okay, so that is what I see looking in here. Okay, I know how to quickly account for these, so I'm not going to waste much effort trying to figure out the impedance of this. I simply want to figure out what current is flowing this way. Okay? So this current Ix, I know that it has to be equal to this Gm, and it has to be equal to V out minus Vg, simply from this. That is, the current that flows through here has to come this way. Gm plus SCGS. So I can expand this out, and essentially I can write that Vg divided by V out is Ri divided by 1 plus SCGS plus Ri. Now, if I put this back together, I essentially have that the output impedance Zx is equal to 1 over Gm plus this 0 and this pole. Okay. Now, there's a couple of really interesting things that happen here. Let's look at the first one. So the first one is if I have the input impedance being very low, and essentially what this means is that the input impedance is less than 1 over Gm. Okay. I'll hit my pole first, okay, and then I'll hit my 0, and then I'll flatten out. So my impedance, that is the impedance that I see of this stage, stays very low. Okay, so 1 over Gm, pole, 0, flat. Now, if on the other hand, my input impedance is very large, that is Ri is much greater than 1 over Gm, I flip around the order of this pole and the 0. That is, I hit the 0 first, and then I hit the pole. So if you think back to what this looks like in terms of frequency response, this looks like an inductor. Okay, that is that as the frequency is increasing, my impedance is going up. So in order to really think about this, we can draw an equivalent circuit for the input impedance being greater than 1 over Gm. Okay, and if we look at this, what we have, we're trying to make essentially here is an equivalent circuit model. Okay, and this inductance, this L, it forms a tank with these CSB and this 1 over GMB. Remember, we left these terms out off of our output impedance Z out, and we computed the impedance looking back here at Zx. Okay, So this inductive equivalent circuit basically forms an LC tank with this CSB. Okay. Now, the exact values of this, we can calculate this inductive value simply from pulling out the plots. And what we do is we take this equation and we separate out the real and the imaginary parts, and we can find the inductive component. The interesting thing is that if we do have this large source impedance, the circuit can be very prone to ringing. Okay, and this is often the case because we use a common drain stage to drive a capacitive load. Okay, so the CSB is often actually a load capacitance in parallel with it, which with this inductor causes ringing at the output. Okay. So a couple of other interesting things, we can think about what happens when we have this parasitic input capacitance CI. Okay. So here, we're not going to neglect this CI term, which was CGD plus CGB that we've neglected in all of our previous analysis. And if we go through this, again, what we see is that we have this 0 here, and the 0 is CGS plus CI, okay? Which makes, again, some more interesting cases on the input impedance of this device. We can essentially have this 0, a pole, and then hit another pole. Alternatively, depending on the positioning of these, we can end up with this case as well under this condition of the input impedance. Okay? So this even very simple stage of this common drain, we can have multiple poles and zeros in the circuit that create very interesting frequency response. Okay? Now again, the thing that I'm talking about here is not the gain of the circuit, it's the impedance of the circuit. So that's why we're looking at Zx of S and over the frequency range. Okay, so let's talk very quickly about a couple of applications that we would typically use these types of amplifiers for. So the first one that's a very obvious one is a level shifter. Okay, so I'm taking this common drain circuit, the bulk is connected to ground, I have some bias current IB that's biasing up this amplifier, and I apply some sinusoidal signal to the input. Okay, essentially I know that my output, that is V out, is going to be VT plus VOV, or VGS, lower than this input voltage. So in this case, I'm actually taking the same signal with more or less unity gain, depending on how we construct this amplifier, or gain of near 1, and I'm level shifting it down. Okay? And this is simply because VGS, that is my bias voltage, is more or less constant. The second application is to use it as a buffer. Okay? So if we think about our common source amplifier, let's say that we had this common source stage here. We have our input signal at the gate. We're taking the output here, and we didn't have this buffer. Okay? So if I didn't have this buffer, I essentially have a large resistance in the load that I'm using to make a high gain for this stage. Okay? And when I connect it to this small impedance, it essentially ruins my gain. And it ruins my gain because the small impedance kills the impedance that this large resistance had. Okay? So if we instead add this buffer in between, we effectively isolate this small impedance from this large impedance. So the input impedance that I see looking into this stage here, it's effectively just the capacitance, which is very small. So I maintain my large impedance. I can have my high gain. Okay? Whereas this stage, I simply take this voltage that's happening here, level shift it to the output, and I can drive this small output impedance. So there's a few issues with this circuit. One of them that we touched upon in homework 1, and that's that there's a couple of sources of nonlinearity. The nonlinearities come from VT being a function of V out. So essentially we're wiggling up and down VBS. And what this does is this is actually effectively changing VT, okay? Which then changes ID and VOV. They all change with respect to V out. Okay? And this problem is only exacerbated once we have small load resistances. The other problem comes back to the same thing that we saw earlier, and that's that the input and output have lower voltage swing. Okay, so taking an example of a newer technology where we only have 1 volt supply, 300 millivolt threshold, and 200 millivolt overdrive, we've effectively used half of our supply headroom, that is zero point 0.5 of this 1 volt, simply for this buffer. Okay? And often that's a steep penalty to pay, so you'll almost never see that circuit. Okay, at least not in that type of application. Where you will see them, though, is when the input signal is very small. Okay, so a good example of that is a preamplifier and a low noise amplifier, where we may be taking a few microvolts or tens or hundreds of microvolts and turning them into millivolts. Okay, in that application, I don't necessarily need a lot of headroom. I don't need a lot of swing. But if I have a large common source amplifier that's producing a few hundred millivolts of swing at the output, this stage is typically not used. So the last application is actually one that we've already seen, and we've even designed circuits with this. It's using the transistor as a load device. Okay, so here we're taking our common source amplifier and we're taking M2 and we've effectively diode connected it. Okay, now the impedance that we see looking up into M2, considering the body effect, is 1 over GM plus GMB2. And so the gain of this is GM1, that is the gain of the transconductance of this device, times the impedance at the output, which is this impedance looking up, 1 over GM plus GMB2, in parallel with RO1, which is much, much, much larger than this effective impedance. So the gain effectively turns out to be GM1 divided by GM2 plus GMB2. Now, the nice part about this, and this is one of the examples that we did in class, and I said this, is that the gain is ratiometric. So ratiometric simply means that by adjusting the widths of these different devices, I can change the gain. The nice part is that it effectively cancels out large dependence on things like supply voltage changing, process, that is Kn and mu of these devices changing, Vt changing, and other temperature changes. A slightly less obvious benefit is that there's actually first order cancellation of some of these nonlinearities. This is something that we'll revisit a little bit later in the class. We'll actually derive the nonlinear behavior of this circuit. Again, one of the disadvantages is that the reduced swing. Okay, so essentially this node, I'm limited to this being VOV plus VT less than VDD, and I have to have 1 VOV to keep this device in saturation, so I've effectively burned 2 VOV plus 1 VT. Okay. So this is not a great circuit for high gain, but it is effective for gains, let's say, less than 10. Okay, so to kind of summarize, we've talked about a common source stage. It's effectively a voltage-controlled current source. It makes a very good voltage amplifier when we put a large impedance at its output. A common gate has a very low input impedance, 1 over GM typically, and it has very large output impedance. We've often seen, or we've seen already a couple of examples of using these devices. One of them is to turn an okay common source amplifier into a better one. Okay. We'll also see that you can use this to cascade this voltage-controlled current source and effectively increase the output impedance. That's what we call a cascoded stage. And then lastly, we just spent the last 20 minutes talking about common drain amplifiers, which are good in the sense that they have very high input impedance and low output impedance. They're effective for shifting DC signals and creating essentially buffers for other signals. All right, thank you, and I'll see you next time.